So another way of talking about uniform circular motion is to talk about it in the frame of rotational motion. And we did spend a good deal of time talking about rotational motion, so we're going to start applying that. So let's talk about there is a classic problem that is set up like this. So there's a table that is frictionless. Okay, here's my table. And there's a hole cut into it. Now from the hole, we're going to have a rope here and a puck that is going to be spinning around the table. And on the other side, we are going to have a mass. So the idea is that I give myself a mass value here. Let's say 3 kilograms. And I'll give myself a mass value here, and we'll say 2 kilograms. And the question we have, I need one more thing, a radius here, and we'll make that 0.5 meters. So the problem itself is this. I need to determine how fast that object needs to spin, this 2 kilogram object, needs to spin in order to suspend this 3 kilogram mass. So that 3 kilogram mass is not going to fall, okay? Like always, when dealing with the uniform circular motion problem, it is a force problem. So I will approach it like a force problem. So the first thing I'm going to do is free body diagram. So there are two objects in this problem. There are the 2 kilogram mass that's spinning and the 3 kilogram mass that's being suspended. So let's start with the 2 kilogram mass. So here is this puck, and we are going to make a claim that the table is absolutely frictionless. Okay, so it has one force down, which we call gravity. It has another force up, which we call normal. And then it has a third force here, which we're going to call tension. Okay? Now at the bottom, we have another object, a 3 kilogram object, and it has two forces on it. One force is gravity, mg, and the other force is tension. Okay? So I can see right now, by just looking at the 3 kilogram object, that tension is going to equal mg. If you need me to do that calculation, you just go the sum of the forces is equal to mass times acceleration. Looking at this object, no acceleration because we want the object to be stationary. So that means the sum of the forces is equal to 0. So at that point, I have T minus mg. Move the mg over to the other side, and I'm left with T equals mg. The great thing about tension is that tension is equal to itself everywhere in that rope. So as long as this is a single piece of rope, that this tension and that tension are equal to each other. So that means that this tension over here is equal to mg, and specifically the 3 kilogram mass. Okay? That's great, because that is the only force that's center pointing, and it's really the only force left as these two balance themselves out. Okay? So that means that I have one force, the force of tension. That force of tension is equal to mg, which is the 3 kilogram mass, but that is also causing the object to accelerate in a circular path. So it's ma, and like always, we're talking about uniform circular motion, so I can do a substitution for a. Here's where this becomes different. So a, we normally say is v squared over r, but if I wanted to express it in circular motion, as a circular motion problem, I'm going to do a substitution. I'm going to say that, oops, I don't want that, I want that. That v over r is equal to omega, angular velocity. Okay? So that means that a is equal to r omega squared. Okay? And this is going to tell me how fast it's spinning. Cool? Now, all I did was, instead of having, I was just like, well, I'll just make this omega squared, make that squared, make that squared. And in order for that to work, I needed to multiply by an r on both sides. Okay, so that way this v squared r squared turns into omega squared, and I'm left with an r on top. That's how I get the a is equal to r omega. All right, now on to the last part of the problem, the plug and chug part of the problem. I have my tension, which is equal to mg, which is the 3 kilogram block. times the acceleration due to gravity, which we know is 9.8, but I'm going to say it's 10. That is equal to ma, and now this is the spinning mass, which is my 2 kilogram object, and we are going to multiply that by a, but I am going to make this substitution for a, okay, which is going to be r omega squared. Okay, so now combining things and moving things around and solving for how fast it's spinning, I'm going to get 3 kilograms divided by 2 kilograms times 10 meters per second is equal to r omega. And then all the way back in my original problem, I said that r is 0.5 meters. So I am left with this. 3 kilograms divided by 2 kilograms multiplied by 10 meters per second is divided by 0.5 meters is equal to omega. Now, I'm lazy. I don't want to do the rest of this math, but it's actually not that bad. 2 divided by that gives me 5. 5 gives me 15. 15 divided by that. So I'm left with 15 divided by 0.5, which gives me 30. All of this gives me 30 equals omega squared. So the square root of 30 is equal to omega. And that gives me how many radians per second that this object has to spin.